The very first time we encountered Poincare inequalities, we used just Lipschitz functions and used subsets of the Euclidean space as examples to illustrate when we do and when we do not have Poincare inequalities. For instance, we can immediately see that if you have disconnected set, we may not have Poincare inequality because you can have 0 here and 1 here. And if you take a ball that intersects both of these on a non-zero measure, then the Poincare inequality will fail because the gradient is 0. However, the left-hand side is not. Then we mentioned that Sobolev-High-Wash functions satisfy the Poincare inequality. And now that we've introduced Newtonian spaces, we can revisit those examples and talk about some geometric properties related to that. Let's recall that we say a space, a metric measure space, satisfies a Poincare inequality if all balls have finite and positive measure, and then for every function u that is integrable over balls, this is enough. We can just also say it's locally integrable. And every upper gradient, we have that the average oscillation of f, or u here, from its average value over the ball is bounded by diameter times the average of LP norm of g to the power 1 over p. And here lambda allows for some dilation of the ball, and c is a universal constant. So if this property holds for all u and its upper gradients, in a space we say the space has the p Poincare inequality, and in all cases p will be bigger than 1 and strictly less than infinity. A consequence of Hölder's inequality is that the average, this is actually one of the easy ways to remember Hölder's inequality in case you take one of your functions to be equal to 1. So you apply Hölder's inequality with 1 as the other function, and to avoid dealing with the measure of the set, you take average. So this is very easy to remember, and if you want to get rid of the average, you simply write 1 over measure of the set, in this case x, that you're integrating over. So this is a true inequality for all p less than or equal to q. Therefore, here by increasing p, we still have the inequality, and as a result, it shows that p Poincare inequality implies q Poincare inequality for all q bigger than p. So this condition requiring a space to have Poincare inequality is actually a condition about the geometry of the space, not a condition about functions, as we do require it for all functions. So it's a connectivity condition on the space, and my very early examples will illustrate that. We already saw that there is no Poincare inequality. So my initial first examples will be R2 equipped with the standard metric and standard measure unless I specify. So let's take this set again. We see that not path connected, then no p Poincare for any p. And then we see that actually we just don't need any kind of path connectivity. We need a lot of connectivity. So if we just join one curve between these two, still no Poincare here for any p. Because, and here's the point, so you can still have a function that is constant 1 here, constant 0 here, And then here, take G to be even infinity. You can afford to just have it here. And then G is 0 back here and here as well. If we test the the upper gradient inequality, we see that this will always hold for any path joining x to y, because if they are in the same side, this is 0 and we don't even need to check. And if they are on the opposite sides, this inequality becomes infinity, and again it holds. However, we see that this G, LP measure of G, is 0 for every P. And this shows that the Poincare inequality will always fail because the right-hand side here will be 0, while the other side can be non-zero if we take a large ball that picks from both sides. This example illustrates that when you are given points in your space, different points in your space, you don't want just any path connecting them, but you want the path that do connect them to occupy some area so that this integral does not become 0. So anytime you can have a set of 0 measure, in this case, sorry about that. So in this case, this set is measure 0, and then an upper gradient supported on that is enough to give us an upper gradient, then we won't be able to have a Poincare inequality for exact same reason. Then we see that for this space, now if we instead actually join them along one point, things get a bit better, because you cannot this time concentrate the upper gradient on a set of measure 0. So here, again, if you try to duplicate the same, you will see that the upper gradient cannot be supported only at 0, because 1 minus 0, if you take x and y on opposite sides, for this to be less than or equal to integral of g, g must be not only supported, it cannot be supported only at 0, so this has to become positive value. And then we see that if you have points x and y here, for g to be an upper gradient, integral of g over this should be 1, over this one integral should be 1, over this one integral should be 1, over this one integral should be 1. And this forces g to be non-zero on a good portion of the space. And this actually, with some calculation, ends up showing that this does support a P-Poincare inequality if P is strictly bigger than 2. So the reason P has to be large is that still we can concentrate G on part that is closer. So G here is very large, and away from here it becomes a bit smaller. So to have integral of g to the p d mu 1 over p be comparable to this side, which is, say, 1, to be able to have this, despite the fact that g is only concentrated very near here, it turns out that we need at least p bigger than 2. Otherwise, we can drive this to be very small and violate that. So that's the idea. So the bigger p helps this side, as we just showed here. The more you increase q, you help that, and it turns out that you at least need p there equal to 2. Okay, A modification of this example, we see that the problem here was that the measure here is very small, and therefore we need to help the function g so that the integral becomes large. Another way would be to adjust our measure, and this is actually a famous example called Gering's bow tie. And if you, instead of Lebesgue measure, put some measure mu, which is some scaling, say theta function of the L2 measure, then by increasing the measure here, you can actually improve the Poincare inequality to anything. Even p equal 1 can be obtained. And this is only saying that, well, by blowing this measure around here, you kind of effectively avoid the pinching of the space by right choice of p. Okay, the other example we had previously again seen was a annulus with this line removed from it. So my space is everything except one line segment. In this case, we saw that there is no Poincare inequality because now you can have a function which starts as 0 here and it becomes 1 here, and somewhere here it can even continuously or Lipschitz way move between 0 and 1 values. The problem balls are something like here. If you take a ball like this, it's 0 on one half and 1 on the other half. And the upper gradient can be taken to be 0 in this case because, I mean, upper gradient, so we can have upper gradient constant 0 around even 3 times large ball, because if you want to test ux minus uy, where x and y are on opposite sides of this ball, we see that there are no path going in the short direction. It's not just in our space. So the path definitely have to start somewhere here and then make the full return. And so G can be concentrated here so that this does become bigger than 1. So this becomes 1. We can have it happen along every path that makes that turn. But on 3b, g is 0. And therefore, again, integral of gp, 1 over p, can be made 0 on that 3b or even 4b. Whatever lambda you fix, you can take a much smaller ball and then make it 0. So we're saying that for every lambda, there exists some ball with these properties that the upper gradient is 0 on that ball. And, well, then this is not bigger than integral average of u over that ball, which is comparable to 1 because it's 0 on one half of the ball and 1 on the other side. And this example is a hint at what is called the quasi-convexity of spaces with Poincare inequality. If you have Poincare inequality, it implies that space is quasi-convex, and that means that there exists some, say, big lambda, such that for every x and y in x, there exists a rectifiable curve such that length of gamma, which obviously a gamma that joins x and y. Definitely its length is bigger than that, but not much more. So up to this universal constant, you can always find a path. So the distance is almost geodesic. That's why it's called quasi convex. Convex would give you in at least Euclidean setting, straight line, which is geodesic. This example here has failed that. Again, the points x and y here are very close. Dxy is very small, but any path that connects them has to make a lot of turn, and the length goes just too much. And this, again, rules out a lot of spaces from being able to have Poincare inequality. So these are just sitting in our two examples. On the positive side, RNs with their usual distance and measure have the best Poincare inequality out there, have one Poincare inequality, right? Which means they have p Poincare for every p then, as one is the best. And we have talked before about Mackay-Tyson weights. There are some choices of functions w, non-negative functions, so that if we scale the Lebesgue measure by that, if we take this to be the measure, then support again one Poincare inequality for classes of weights, for certain classes of weights, including Mackay-Tyson weight. I have made a lecture about them in this series. So that's moving a little bit away from Euclidean settings. Manifolds, some manifolds, of course, some manifolds support Poincare inequalities. The case of compact versus non-compact is quite delicate, and curvature comes into play some role. Sub-Riemannian examples will be Carnot groups, in particular Heisenberg groups. Support one Poincare inequalities. And for example, H1, the interesting thing here is that it's not with the, of course, its intrinsic Carnot distance and its Haar measure, which is just H4, and that coincides with Lebesgue 3 measure, is not a manifold. So we know that Hn, and in this case H1 for instance, does not embed in a Lipschitz way in a bi-Lipschitz way in any Euclidean space, even if you allow a very large dimension. So this is in contrast to Whitney embedding or Nash embedding, that any manifold embeds in large enough Euclidean space, but H1 has this fractal nature to it that stops it from embedding into any Euclidean space, even in R 10,000. So this is a very non-Euclidean example. At this point, even the metric is not comparable to Euclidean metrics. But still here we see that the dimension, the Hausdorff dimension of H1 is 4, which is strictly bigger than its topological dimension, which is 3, as it is homeomorphic to R3. Then Laakso gave examples, and then later Bourdon and Pajot, they gave examples of spaces, even Alfors regular spaces. So Q Alfors regular. Usually Poincare inequalities are paired with doubling measures or Alfors regular measures, which means that measure of a ball of radius r, independent of where the center is comparable to r to the power q, where r is less than diameter of the space. So examples of Alfors regular spaces with even best Poincare inequality, with one Poincare inequality, that where, so they gave such examples where q is not even an integer. So the being Alfors regular with one Poincare is very strong on a space. We have a lot of potential theory on them, and moreover we have what is called Cheeger differentiability theory, which is quite surprising because it almost tells you that such metric spaces have linear structure like Euclidean spaces, which allow differentiability in like different Rademacher differentiability of Lipschitz functions, for instance. So that theory lets you differentiate Lipschitz functions in a genuine way, not just upper gradients, which are absolute values of, in a sense, derivatives, but actually to obtain derivatives. And in light of this, having examples with non-integer dimension is quite surprising. The other example, which is my last that I kind of like, and that's why I want to mention, is due to Heinonen and Koskela in their ACTA paper, which I talked in the Beamer presentation that I had, is where they actually introduced this notion of Poincare inequality, is when you glue two spaces that have, say, one Poincare inequality along a smaller dimensional set. And the simplest case is, well, you have two boxes, two pieces of R2, which each individually supports a one Poincare inequality, but then say you glue them along a Cantor set. So you take a common Cantor set on edges, and you glue them along there and equip them with the induced measure and metric. And the metric will be the infimum of the length of all paths that connect the two through the, of course, identified set. And if you want to draw this so that it kind of embeds in R2, at these 2 points, the top and bottom are identified, but somewhere here in the middle, where the space is not identified, we have two copies of the same line segment. So we can introduce a rupture here so that it has two copies. So this bending is, of course, forced to be able to draw and embed. And then here again, something like that. You can also do circular arc if you want. So this is only representation. So away from the Cantor set, you have two copies, but on the Cantor set, they get glued. And then for this example, we have P Poincare inequality if P is bigger than 2, the dimension of these spaces minus the dimension of the common Cantor set that you glued along. This I wanted to mention because if we go back to this issue of how much volume do you lose when you connect them. So with the example here, glued along just 1 point, we saw that P had to be bigger than 2 because that's basically the compensation for how much volume you lose. But in this example, although my picture doesn't show it, the Cantor set, although has measure 0, it does allow distribution of this volumes. So there are so many different ways to connect from X to Y, and each collection that you have picks up some volume at different counterpoints. And the volume loss is not as severe as the example with 1 point. And that improves the Poincare inequality a little bit, so you get from bigger than 2 to bigger than 2 minus something. And this is sharp. You cannot do better than that one. Okay, so as I have mentioned before, but for completeness, I must say that doubling, so the why care about Poincare inequalities, if you check the recent articles, their abstracts or titles from MathSciNet, say, you see a lot of recent work on spaces, the so-called PI spaces, spaces that have a doubling measure and a Poincare inequality, especially one Poincare inequality. And if you have these two, then there is a rich theory of infinitesimal calculus available. You can do a lot of potential theory on metric measure spaces. You can basically do the minimization questions and solve PDEs, basically. The theory of BV functions becomes interesting, and many more. So it's a big deal to know more about the spaces that support Poincare inequalities, to find more examples. In my Beamer presentation, I mentioned its connections to quasi-conformal theory and whatnot. Indeed, one of the research projects that I'm currently working on has to do with attempts to prove that a certain example does support Poincare inequality, and we want to find the sharp exponent there. Maybe more on that later. So that brings me to the end of the story of analysis on metric measure spaces for now. And I have already posted a poll under the community. So please go and vote which one of these topics you would want to see next. We can go and talk about Heisenberg group a little bit in depth, talking about its sub-Riemannian structure and Carnot structure, and more importantly, to distinguish what comes from its sub-Riemannian geometry and what comes from it being a Carnot group. The other topic, now this is kind of embarrassing because, okay, no, I have my paper here. So the other option is to talk about the area and coarea formulas in the sense of geometric measure theory. We've covered them extensively in this channel for Lipschitz maps between Euclidean spaces, but this time for maps that go from Rn or subsets of Rn into arbitrary metric measure spaces. This is a theory developed after 94, and mostly by work of Kirchheim and Ambrosio Kirchheim. And this was the topic of my PhD work, so I can tell you a little bit about this. And then if you're trying, if you want some kind of professional development topics, we can talk about the issue of writing. I can share my experience with good practices in writing, what to avoid. And here, of course, this is a general thing, but we can focus on just writing thesis. Why do we write thesis? What to focus on? What is the goal? How to write research papers, how to read research papers sometimes. And also when you apply for jobs, of course, the first research statements you want to write, you're really unsure what to put in them. One of the most annoying things is no one actually shares these. And you write something and you're not sure if it's completely in the wrong direction, or is it sufficient enough? Is it too long? Is it too short? How many pages should it be? Should you mention this or that? So if you have such questions, let me know, and then we can also move toward that direction. Thank you for watching this video. As usual, please don't forget to subscribe. That helps promote the content, and see you soon.